I am trying to make sure we go through this analysis for the equilibrium. It is identical to what you did in the pre-lab, except we're pulling it all together from one set of data. In the pre-lab, I kind of broke it up into steps. Same idea though. I'm going to show you a step through of what you would do with data. It's a different reaction, so the K and the setup is slightly different, but we can get the same idea. It would have begun, so in this particular case, my reaction is silver ion plus 2 cyanide ions makes this silver cyanide complex of silver cyanide negative ion complex. And supposing, I'm pretty sure, although I think that silver cyanide might be active in the infrared range, I don't think you'd actually get a color on it. But I'm making up a chart. I don't even know what wavelength. I made up these numbers. So I make some standard solutions of this ion complex, and I measure the absorbance so that I know how his absorbance relates to the concentration. This is what you did in part A. I'd make my graph. Note that on my graph I have a nice linear relationship, that's what I expect, and I get a line fit that the absorbance is equal to 258 times x plus 7.46 e to the negative 3. So that is now going to be my relationship that relates concentration and absorbance. Now, this is my second part reaction. I'm going to mix 6.2 milliliters of this silver nitrate solution with 4.5 milliliters of 0.004 potassium cyanide solution, dilute it to 15 milliliters in a volumetric flask, and then I take an absorbance, and the absorbance is 0.126. So what do I do with all that? So first I want to build a nice table like you would in class. So we know that the initial of the ion and the initial concentration of the cyanide, the initial concentration of the silver cyanide ion would be none because the reaction hasn't begun. Initially means before the reaction began. During the reaction, I don't know how much reacts, but let me say X moles of silver ion reacts. If X moles of silver ion reacts, that's going to deplete the initial supply by X moles, so I do minus X. Since this requires 2, in this case, 2 cyanide ions, it would deplete the cyanide ion by minus 2X. And then for my silver cyanide, I make one of those, so it would increase by X. So at the end, I know my equilibrium algebraically is the initial of the silver minus X, the initial of the cyanide minus the X. Let me just clean that up. That should be initial concentration minus X. All right, and the silver cyanide would be X. Okay, now let's get into the specifics. So let me kind of run down to here. Okay, so now again here I've recorded this information. I can calculate the information of what is the initial by this. I changed some of these numbers, 6.2, and this is 0.004, sorry. All right, so I'd have my 6.2 milliliters, since this is my silver nitrate is my source of silver ion, 6.2 milliliters times the 0.00150, that's my M1 and my V1. My M2 is the 15 milliliters, because I diluted it before I started reacting it. When I mix them together in this 15 milliliter flask, they start to react, but it's actually kind of diluted the initial concentration. So initial means just not initial in the stock bottle, but initial before the reaction began. And similarly for the cyanide ion, it's 4.5 times 0.004 divided by 15. Also, I know about the concentration of the equilibrium concentration of the silver cyanide ion from the absorbance. So I can use that spectroscopy, the 0.126 absorbance minus the 0.00746, that was the y-intercept, and then I divide it by the slope, that 258, so I'm solving for that concentration. Down here, if I did it, it would be, so it's 0.000620 and 0.001200, and the equilibrium concentration is 0.000459. So I now have my actually I have all my initial concentrations, and I have one of my equilibrium concentrations. But remember, this value here in this box, algebraically, is equal to X, right? It's 0 plus X would be X, right? Up here, we said, hey, that's what that is. So I know X. This is my X, right? Let's kind of make that nice and red. That's my X. So now I can go back and backfill. This would be 0.00459. This would be negative 2 times 0.00459. This would be negative 0.00459. So I come down here, and that's what I do. So I put those numbers in. Let's clean this up. Make them the same number. It's just easier if you make them all 6 decimal places so it all lines up and it makes sense. And so then, because I know the initial and I know the x, I know the change, I can just do a manual subtraction, and I can add these together to get my equilibrium concentration for my silver and my cyanide, which I do. In this particular case, once I have these 3 equilibrium concentrations, I can solve for K. In this particular case, because the stoichiometry is a slightly different reaction, the expression would be the product, the concentration of the product. There is no coefficient, so it'd be raised to the 1 power, divided by the concentration of the first reactant. There is no coefficient, so it would be to the 1st power, times the concentration of the second product. There's a 2, so I would square that concentration. So this is my formula, 0.000459 on the top, divided by 0.000161, also divided by 0.000281 squared. I calculate that out. I get this really big number. If I round it to 3 sig figs and put it in scientific notation, I get 3.62 times 10 to the 7th. That's what you're going to do. Your reaction's different. It's actually a little easier. You don't have any 2s. You don't have any stoichiometry. But you're going to do the same thing with your data. Shouldn't take too long. We're really kind of wrapping up some things we did in the pre-lab and things we did in lab 1. So it should be a pretty easy lab.